Hi, welcome to the fifth session on inner product spaces. Uh, yeah, we proved the Cauchy-Schwarz inequality. Remember, till now we are confined, we have restricted ourselves to real inner product spaces. Okay, we are not defined inner product space on complex vector spaces. Okay, and using Cauchy-Schwarz inequality, we also showed how to define an angle between two non-zero vectors. Using this notion of angle, we can define when two vectors are perpendicular to each other, right? And then using that concept, we can try to say what is how to define how to project a vector, okay, orthogonally onto another vector. Of course, both are non-zero. Okay, these are the very beautiful geometric thing which we can explain and derive, okay, from our knowledge about geometry and various things in real inner product spaces. Whereas in the complex inner product spaces, as you are going to see, whatever expression we are going to get for this, we will take it as a definition for complex inner product spaces. There is no geometric intuition at all. Okay, this is some kind of a disservice if you start with complex inner product spaces, okay, without mentioning about the geometric insight which you get from real and inner product spaces. Okay, I believe it's a disservice to the student community. What most books do that, what to do. Okay, so let us get started. Okay, so this is the thing, and as usual, this is my channel, this is my email ID. You can download the list of videos from my channel from this site, or you can scan it. This site will come, then you have to search for a list of videos, and it will be good if you're a beginner, if you want to learn a subject very thoroughly from the beginning. Okay, the list will give descriptions. Okay, and what is the first, okay, it is broken into various chapters like playlists, and each playlist in the serial order, which is the first video, second video, third video, so that you will learn it much better and a very systematic way. So by the way, today I uploaded the latest uh, list of videos which incorporates the last playlist, namely infinite series. Yeah, okay, now come back. Today's topic is orthogonality. So let us quickly I started recording. Okay, good. Okay, so let V with this be an inner product space over R, right? Then we showed that for any two vectors u and v in V, take the inner product uv. This is a real number. Its modulus will be less than or equal to norm u into norm v. This is for all u and v. In particular, u and v non-zero. Then let us look at this number, inner product u v. This is just inner product by norm u norm v. This is less than or equal to 1 and greater than or equal to minus 1. Therefore, there is a unique theta where in 0 pi, so that cos theta equal to uv by norm u into norm v. In particular, if norm u equal to 1 equal to norm v, then u and v are called unit vectors. Then cos theta is nothing other than inner product uv. Is that okay? Right. Notice that this is true for all u and v, but to define cos theta, I need none of the vectors u to be 0. Okay, both are non-zero. Right, very good. Now suppose I have two vectors. Let me, instead of u and v, I will hereafter I will use u for unit vector. So let me start with the u and v, non-zero. Okay, right? When do I say v and u are perpendicular to each other? That is B is perpendicular to W. When do I say that? You know that from our geometry, if the angle between them is pi by 2, as you may say 90 degrees, etc. Alright, but if it is pi, if the angle between them is pi by 2, then what is cos pi by 2 or cos 90? This is 0. But what is cos pi? Okay, there. So the angle between them, suppose theta is the angle between V and W, then cos theta is inner product B W by norm V norm W. And if the angle between them theta is, they are perpendicular to each other, then this must be 0. And remember, norm U norm V are not 0, therefore that means inner product BW should be 0. Right? So now this suggests we make a definition in an inner product space this. Okay, notice that I am not imposing any condition on dimension, it may be infinite also. Okay, and let V and W be two vectors, then I say V and W are orthogonal or perpendicular. This is a very fancy word which simply means perpendicular to each other if inner product BW is 0. Is that okay? Now, what are the things you should notice about my definition? When I want to define angle between two vectors, I wanted them to be non-zero vectors. Right? If they are non-zero vectors, if the angle between them is pi by 2, then I found cos theta, which is given by inner product BW by norm V norm W. Okay, that must be 0. And hence we proved inner product BW must be 0. Right? Conversely, if inner product BW is 0, therefore cos theta, which is inner product BW by norm V norm W, will also be 0. Therefore theta must be pi by 2. Right? So in the case of real inner product spaces, we know, okay, here two vectors are perpendicular to each other or orthogonal to each other if and only if inner product BW is 0. Right? Okay. Now, so far I said something about non-zero vectors, but notice that here I am saying V and W are any two vectors. I say they are orthogonal to each other if inner product BW is 0. In particular, the 0 vector is always perpendicular to V for every V in V. Right? So we are including 0 vector also to talk about orthogonal vectors. Is that okay? Very good. Okay, so how does the picture should look like now? Therefore, if V and W are orthogonal, okay, that means if this is, okay, let me rewrite it. Suppose this is my V and this will be my, this may be my W. So they are perpendicular to each other. So in case you are thinking in terms of an axis, okay, this may be my V and this may be my W. So this is V, this is W. Okay, right. So make sure, for example, in the case of R2, just you can quickly check example. Let us look at an example. In R2 with the standard dot product, right? Let us look at the vector E1 plus E2, E1 minus E2. That is going to be, this is 1 1 and this is, okay, 1 minus 1, okay, E1 and, okay, sorry, okay, minus E1 plus E2. Right? They are orthogonal to each other. Why? E1 plus E2 dot product with minus E1 plus E2. Therefore, E1 into E1 with a minus sign plus E1 dot E2 and then E2 dot minus E1 plus E2 dot E2. Okay. You understand this? But this is already 0 because 1 0 dot product is 0 1. Okay, these are 0. Okay, this may be minus 1 0, but it doesn't matter. But let's look at this. This is u2. Okay, minus u1 times u2. Sorry, minus u1 times u1, which is minus 1, and u2 times u1 is plus 1, therefore it is 0. Okay, so this is orthogonality for you. So pause, review, proceed. So given a non-zero vector v in AB in R2, this is non-zero, find a vector W which is perpendicular to V. Find. Okay, it's extremely easy. Think about, okay, you know that. Okay, yes, and also if you've seen my linear maps, I define rotation maps also. Okay, these are also, this is how you relate, right? So you rotate, this is my V, okay, this is my AB, okay, maybe I should write it AB column vector and rotate it by pi by 2. Pi by 2. This is a rotation. So rotation matrix, you know how it is given by, okay, what is the rotation pi by 2? That is cos theta minus sin theta cos theta, that should act on AB. So that is going to be what? This theta is pi by 2, therefore it's 0, and minus 1 1, and therefore this is going to be AB is minus BA, right? And this should not be surprising. See, the maths is fun if you really want to think. Let us look at the equation of a line passing through origin. You will simply say ax plus by equal to 0, right? Then let us look at therefore the point minus BA is there, and the point, this vector AB is the normal to the line, and this is the point on the line, right? Therefore they have to be perpendicular to each other. Yeah, see, this is a lot of geometry. You see that these are the things which you miss in pure algebra courses. Okay, this is enough. So we will go to the next step. Okay, the next step is I want to define orthogonal projection. So let us look at, in the case of R2 with a dot product, okay, suppose I have a vector, let us say this is the vector, okay, AB, then you know what is orthogonal projection, right? That is project onto the perpendicularly onto the x-axis. This is the orthogonal projections. You get this. This is a comma 0, and you project here, and this is 0 comma b, right? So what are you doing? You took a vector a comma b, you are projected onto the x-axis to get a vector a comma 0, and you projected the same vector ab onto the y-axis to get another vector 0 comma b, right? Right, all you following? Right. Okay, now what are we trying to show? This is what we call orthogonal projection. How do I get it? Okay, so how do I do that? So let V be an inner product space now, real of course. Okay, let VW be, okay, let U be a unit vector. What is meant by unit vector? Norm of U equal to 1. That is inner product U equal to 1, right? And V be any, W be any, sorry, let V be any vector in V, right? This I will draw the picture. Okay, this is my V and this may be my U. Okay, this is not R2. Okay, now this is my vector V. Then what do I want to do? I want to orthogonally project it. Okay, so I am looking after this particular vector. Okay, this vector, okay, is what I call V orthogonal projection of V onto the unit vector. All right. Now how do I find it? So notice that call this a vector as, for example, let's say call this as a vector as w. Okay. Now w is a scalar multiple of u. Right. Now how do I find this t? Now w is in the direction of u. So to notice w, what all I need is the length. Right. You understand? Length of w. That is equal to t. Notice that my w is in the direction of u, therefore the t will be positive. Therefore that's why I don't write mod t. Okay. If you have problem, just assume that, no problem. We'll come to that in a minute. Okay. Now how do I find this t? So what is t? But that's very easy, because now I can use the way I define trigonometry. See, let us look at this angle. Suppose this angle is theta. Right? Now what is cos theta? Cos theta is this length of this, that is mod t, and that is norm of w. Okay, this is the length of this, so this is norm of w. Okay, and that divided by norm of v. Right? Therefore, but this fellow is just a t and this fellow is norm v. Therefore my t is nothing other than cos theta into norm v. Yeah, so what we have is a t equal to norm of vu by norm of v into norm of u into norm of v. Therefore norm of v cancel. This is u equal to 1. Therefore this is v inner product u. Therefore our vector w, which is t times u, is going to be inner product vu u. Okay, so this vector is called the orthogonal projection. V onto u, the unit vector u, w, is called the orthogonal projection. Okay, let us look at, make sure that we understand properly. Okay, let us look at R2 with a dot product. Right, now suppose I have like this, something like this is 4 and 3. Right, what will be orthogonal projection onto this unit vector where u is u1. Okay, this is u1, which is 1 comma 0, this vector. Okay, that is given by, therefore we know that this point orthogonal projection will be 4. Therefore I should expect it to be 4 0 in the direction of e1. Right, let us make sure. What is w? That is inner product of 4 3. Okay, dot product of 4 3 with the vector e1, which is 1 comma 0, which is 4, times e1 times 1 comma 0, which is 4 comma 0. So we got it. And similarly, suppose my u, okay, the other unit vector is, let us say 0 comma 1, which is e2. Then what should I expect? Let us go back to the same thing. Let us look at it. This one will be, maybe I should use it slightly different color. This will be 0 comma 3. This will be the orthogonal projection onto the y-axis. Therefore this will be, again this, call it as some w dash. So orthogonal projection w dash of the vector 4 comma 3 onto this will be given by inner product of 4 3 with 0 1 times e2. This is 3 times 0 1, which is 0 3. Do you see that? So this is the orthogonal projection. So please pause, review, proceed. So let us summarize. So given two vectors v and w in an inner product space, v is orthogonal to w if inner product vw is 0. That is our definition. But we just why this definition came? Because we are able to motivate it geometrically. Second thing is, okay, if u is a unit vector and v is a vector in v, then orthogonal projection of v in the direction of u is given by, let us call it orthogonal projection. Let me denote the name. This is PUV. That is projection of v in the direction of u. Projection P for projection of v in the direction of u, right, is given by PUV is inner product VU with u. Okay, so pause, review, proceed. Okay, now let's go ahead. What are the things you can observe from here? Okay, first thing is, did you notice that, see, let us look at the picture again. This may be any inner product space B. Okay, I am just drawing as an R2, and this is my V, this is my U, and I am projecting it. Notice that, okay, this vector is this vector, right? This is my P U of V, right? So when I look at P V minus P U of V, in this I have to put this vector. Okay, this is the vector minus P U of V. Where will I land? I land in this vector. This is the vector which is V minus P U of V. I will explain everything in R2, but please understand, right? The picture shows something very interesting. What do you see that? See, this vector what we got, V minus Pu of V, will be perpendicular to the U vector. These two vectors are perpendicular. Do you understand this? That is P V minus Pu of V is perpendicular to V. The picture shows, sorry, perpendicular to U. Right? Yeah. Alright, now let us check it. Okay. So what is that I want to do? Okay. Claim, okay, the vector V minus Pu of V is perpendicular to U, is orthogonal to U. Now how do I check orthogonality? I have to look at their inner product. That is to show inner product of V minus Pu of V inner product with U, is it 0, right? But now you know, all of you are very adept. This is VU minus Pu of V inner product U, whether that is equal to 0. So this is VU, no problem. What is Pu of V? This is VU minus what is Pu of V. So again you should remember, from V you throw away the orthogonal component Pu of V. Just keep the picture in mind. Don't worry about the formulas. Formula will come automatically. Therefore, sorry, VU U. This is the orthogonal projection of V onto U. So you throw it out of V. Therefore it is V minus inner product VU U U. Notice that this is just a thing about a scalar, whether it is equal to 0, right? But this is easy. This is VU minus this VU inner product. This is a scalar that comes out. That maybe you can do it. Okay, so what do I have? VU minus this vector, whether that is 0, I'm just doing that. Okay, but that is going to be VU, and this is plus VU U. Okay, I'm running into problem. B minus PU of V is it perpendicular to U, therefore B minus PU of V, VU. Oh, sorry, I'm sorry. See, I think I'm not focused today. V minus PU of V inner product U, whether it is 0, but that is VU minus PUV U equal to 0, but this is VU, and what is minus PU of V? That is inner product VU U with U, whether it is equal to 0. But notice that this is a scalar, therefore it is VU minus VU, and inner product UU is 0, but U is 1, therefore it's correct. Okay, I'm sorry for the goofing. I forgot that I already wrote V minus here and I substituted the wrong formula here. Are you following? Okay, this PUV is just this alone. Okay, yeah. Okay, pause, review, proceed. So what have we shown now? So we have shown purely algebraically that if U is a unit vector and V is any vector, we define what is meant by the orthogonal projection, that is by definition inner product of V with U in U. So keep the picture in mind. This is B, this is U, this is the angle theta, this will be okay the length of V times cos theta. This length will be this. That's all we used. Okay, and cos theta formula you substitute and you make use of the fact U is unit vector, right? This is norm V into cos theta is VU by norm V into norm U, which is 1. This cancelled, therefore I got it, right? And it must be a vector, therefore it's which in the direction of U. So we wrote it. I'm just explaining this so that to show you the simplicity. So whenever I do, I always revise 3 or 4 times like that so that it becomes part of me. You should also do the same thing. You should not think once I had understood that's enough and leave it. Okay, right. Next, what did we do? From the picture we looked at this PUV, that is from V you throw away the orthogonal complement. Okay, this is the picture now I have from here. Now this is the one. Now I take it. Okay, this is the vector minus PU of V, and this is the vector which is V minus PU of V. This vector seems to be perpendicular to this vector, that is U direction, right? We wanted to check whether it is true. So we check that this is perpendicular to U. That is that clear? Okay. Is there anything more I have to say? Let me just check it. Yeah. Right. Now let's make some simple observations. If okay, let's suppose, okay, now let's look at orthogonal projection of V along any non-zero vector. So U is not necessarily okay. Now remember, it's along the direction, therefore direction is the same the moment I see. If you give me a vector U, okay, and let us look at, let me just say along a non-zero vector, maybe I should use something else, W. Okay, then let's look at U by this. Okay, this is the vector, so this is my W. Okay, then let's look at this. I am assuming norm W is greater than 1, then this will be U, which is W by norm W. So the vector u will be again in the same direction of w. It's not in the opposite direction of w, and its length will be 1 because I divided by the length. For example, if the length of w is less than 1, suppose this is my 1, length of w is this, then this will be this will be my u, w by norm w, because the length has to be magnified. Remember, 1 by norm w is less than 1, therefore 1 by norm w will be greater than 1, therefore the length will be greater. Okay, learn to think of this thing. So simply do not work with symbols. Okay, right. So therefore, what do you think I should do? Therefore w is a non-zero vector, therefore let us look at w by norm w. Then I know what is meant by projection of the vector v in the unit direction. This is given by vu by u. But remember, okay, either I again keep the picture in mind, do not get confused. So this may be my w, this may be my u, and this may be my vector. So this may be my vector v. When I orthogonally project, this is the vector I'm going to get. This is v. Okay, either in the direction of w or in the direction of u does not matter. Do you understand that? This is w, this is u, this is v. It does not matter. Do you follow that? Therefore I should expect this is same as v. What is u? W by norm w into w by norm w. Therefore we have the formula for the orthogonal projection of v onto along the direction vector w is given by pw of v is inner product of v with w and w by norm w squared, which is the w by w. Just make sure you got it. You see that dw, there is a w, norm w squared, but norm w squared is inner product vv. Okay, keep this in mind. Pause, review, proceed. Okay, right. Now again you may ask, okay, suppose v minus pw of v, is it perpendicular to w, not with respect to u? But that's very easy. Okay, believe me. Okay, it's a question, but the answer is easy. But okay, let us make some observations. Suppose v, let us take, now let me use x and y to be a vector in another product space, and suppose if x is orthogonal to y, implies x is orthogonal to ty for every real scalar t. Why? That's because this may implies x inner product y is 0, right? But x inner product ty is t times inner product xy, but therefore it's t times 0, which is 0. Okay, is that clear? Right? Okay, right? Okay, now let us look at, now what is the relation between w and u? Okay, w is nothing other than norm w times u, therefore these are scalar multiples of each other, right? Are you following me? Please make sure, right? If you want, I will give you a direct proof. Let us see. See, v, is it sorry, v minus pw of v, is it perpendicular to w? Okay, let us do that. It's very simple. V minus pw of v. This time I hope I don't make that mistake. That is inner product vw minus inner product pw of v with w. But that is equal to vw minus, what is pw of v that we saw? It is vw by norm w squared right, into V. It's in the direction of V. I hope I wrote it correctly. I'm sorry. See, yeah, in the direction of W. Yeah, in the direction of W times W, right? But that is V inner product W minus this scalar comes out V W by norm W squared comes out. Then I am left with W W, but that is norm W squared. This, therefore this is 0. So we proved it. Okay. I'm going fast perhaps, but you should go and check it on your own. It's all easy. That's a way you can gain confidence. Okay. So pause, review, proceed. So this should be easy for me because what I saw was the orthogonal projection is independent of the non-zero vector in the direction. It could be u unit vector, it could be any w which is a scalar of u, but orthogonal projection of a vector b onto this, it's actually a projection onto the line spanned by this vector. You understand this? This is my, let us say this is my w, this is my u, and this is my vector b. Orthogonal projection, okay, depends only on this line. Okay, but then it's given in a particular direction. Okay, namely whether it's in u or minus u, because if it's minus u it may be different. Okay, please follow that. And I will just stop with the last observation. Notice that in the case of R2, when I took AB, this will be my A, this will be my B, this is 0 comma B, this is A comma 0. These two vectors are perpendicular to each. This vector, let me just give some name. Okay, this vector and this vector are perpendicular to each other and their sum is A comma B. Do you understand that? So my A comma B was, okay, orthogonal projection of, call this as B, and my u, let me say 1 comma 0, orthogonal projection of this vector plus B minus orthogonal projection of B. This sum, right? This sum get cancelled, I get a V. This is your V. So there is nothing wrong. But the very interesting thing is this vector and this vector are perpendicular, orthogonal to each other. So what do you think I have done? Given a vector in R2, I wrote it as a direct sum of two vectors, as a sum of two vectors which are orthogonal to each other. Right? Now the same thing is true. So let V be an inner product space, and okay, let U be a unit vector. Let me stick to unit vector so that life will be easier for us. All right. Then we have V as orthogonal projection of B on in the direction of U minus B minus, this is just ordinary minus inner product, sorry, PUV minus PU. And what we know is these two are perpendicular to each other. This and this are perpendicular to each other. This we had already seen. This is plus, not minus. Right? These are perpendicular to each other, orthogonal to each other. Right? Now, therefore, call it as x and y, then x and y are perpendicular to each other. Now I am claiming norm b squared is same as norm x squared plus norm y squared. Okay, this has not, okay, you can use the formula, but there is a very smart way of doing. With that I will stop. Okay, you can use the formula to prove, use the formula for x and y to check this, but we shall prove a more general observation. Suppose v is x plus y and x and y are orthogonal, okay, then norm of x squared equal to, sorry, norm of v squared equal to norm of x squared plus norm of y squared. But that's very easy, because how do I check norm of x? This is what is a Pythagoras theorem. Why? Norm of x squared is x inner product xx, sorry, v, sorry, norm of v squared is inner product vv, but inner product vv is x plus y, but now you are all very good at this. So this is what, this is inner product xx plus inner product x with y plus inner product y with x plus inner product yy. Okay, but remember, inner product xy, inner product y, these are 0 because they are orthogonal to each other. Therefore this is norm x squared plus norm y squared. Do you understand that? Yeah, that's what we proved. Okay, so the last thing, okay, this is a again in the trade secret. In any inner product space, okay, whenever we have two linearly independent in W, okay, we are working in a Euclidean geometry. Okay, you may not understand, you may not fully appreciate this point, but keep this in mind. This is a very vague statement. As I go along, I'll bring back this, okay, bring it to your attention. What are the places we are using this? Okay, I hope all of you enjoyed. Please go through it. I'm sorry for one small goofing on the way. Okay, right. Usually it doesn't happen if I work in a blackboard, but anyway, all right. Okay, I hope you enjoyed. There is a lot of geometry, and and you should please, if you have access to my book Linear Algebra and with Geometric Approach, please read that with better pictures. Okay, my pictures are not that good. Okay, the computer drawn pictures, you will be able to understand much better, and it will consolidate your understanding again. Okay, I hope you enjoyed. We will meet again. But remember, whatever I did today, so essentially it looks as though we are dealing with only two-dimensional thing. That's the important thing. Just go through it. Every time I'm working with only two vectors, so my R2 is good enough and Euclidean geometry is good enough. Okay, but remember all the things which you proved us with a formula, with algebraic expression, using the properties of inner product, they are all rigorous. But how did I arrive at the formula? The formulas arrived at looking at things geometrically. Okay, now you can erase the geometry. You can work with only the formulas. That's what usually algebra books do. And students think why it's called orthogonal in a complex inner product space. When you have, there is no geometric interpretation. It is, you have to take it. Okay, you will understand. Please appreciate. Go through. We'll meet again.